Welcome back to an introduction to climate change science, which I, Robert Bourgeois, have prepared as a requirement to complete the 2015 PEER Summer Institute at Yale University. That stands for Program of International Educational Resources. And the topic of that workshop was Global Challenges, Climate Change, and Food Security. I'm going to switch to a new slide to where we were last time. We ended up speaking about the greenhouse effect, which refers to the fact that gases in the atmosphere trap some of the radiation that comes from the sun and bounces back into space, but some of it is trapped here on Earth by virtue of the fact that gases within our atmosphere do not permit that radiation to leave the atmosphere and enter into space, and that keeps us warm on Earth. To give a comparative perspective, let's look at three planets. We're the third planet out from the sun, Earth. The closer planet, which is near us, is Venus. Venus is 25 million miles closer to the sun, and it's only a few degrees warmer, and it was so from its creation when the solar system was created. But that additional warmth ultimately resulted in the loss of water on Venus. The oxygen atoms were left after hydrogen was released into the atmosphere. The oxygen combined with carbon to form a dense atmosphere of carbon dioxide around the planet Venus. 96% of that atmosphere is composed of CO2, or carbon dioxide, and that keeps it very hot. It is at 420 degrees Celsius, not Fahrenheit, but Celsius. That's hot enough to melt lead. So it's a kind of cautionary tale on what can happen as a self-generating process if the surface of a body in space warms up enough. Now, that's one planet closer. One planet farther out is Mars. That has a very thin atmosphere. Almost all of its carbon dioxide is in the ground. The average temperature on Mars is minus 50 degrees Celsius, so it's a frozen waste. Our atmosphere has 0.03% of the atmosphere is composed of CO2. The average here is 15 degrees centigrade, which is equivalent to about 59 degrees Fahrenheit on the whole Earth. Now that's an average for the whole Earth. There are extremes of heat and cold by our standards above and below that temperature. Now we spoke of climate as the average of temperature and precipitation over a long period of time, typically 30 years. We talked about the impact of the sun and the orbital parameters of the Earth on climate. The climate is made up of a number of systems which are components of the Earth's overall climate system. One is the cryosphere, and that consists of polar ice caps, sea ice, permafrost, and seasonal snow cover, and mountain glaciers. So that's the cold part, the coldest parts of the Earth. Then there's the geosphere. Geo means Earth, so that's the land surface of the Earth. There's the hydrosphere, which consists of all the water, oceans, lakes, and rivers. And there's the atmosphere, which is a thin layer of air around the Earth, which contains oxygen and other gases. You could compare the atmosphere to its relationship to the Earth as a little bit like the skin of an apple to an apple. It's a thin little envelope. Now the biosphere is a sphere which contains the ecosystems. That is to say, those systems of living organisms which interact within the whole web of life. And the biosphere overlaps other parts of the climate system. The biosphere contains, for example, the oceans, the lakes, and the rivers, because there's life there. Bios is Greek for life. It overlaps the geosphere because there's life in the Earth, especially those fertile parts of the Earth. And there's life in in the cryosphere, the cold parts of the Earth as well. So they overlap. Now, these 5 subsystems interact all the time in a nonlinear fashion. And I don't expect you to be able to absorb all of this complex picture here, but what it's showing is atmosphere, cyrosphere, biosphere, hydrosphere, all interacting, and it does so in unpredictable. They do so in unpredictable ways, and as I say, in a nonlinear fashion. So it makes the study and prediction and modeling of climates very complicated, and it's one of the reasons that it's so difficult to predict the weather, and it should make us feel quite amazed that the weather predictions are as good as they are. I will stop part 2 here, and I'll continue with part 3 in the next screencast.